Welcome to AI Paper Podcast, where we bring you the cutting-edge insights from the world of AI research, distilled and made digestible. Today we're tackling a fascinating and really fundamental challenge in AI. It's about enabling machines to truly understand and interact with our complex physical world, all from visual input. I mean, just imagine the sheer complexity of reconstructing an entire 3D environment accurately and stably from just a continuous video stream. And while our state-of-the-art models are, incredibly powerful at this, they often hit a significant wall. They're slow, they devour memory, and they simply can't handle this really long video sequences needed for large-scale applications.
Precisely, and that's really the grand mission of the paper we're diving into today, Fast-VGGT, Training for the Acceleration of Visual Geometry Transformer. It's all about breaking down those critical barriers to scaling 3D vision, making these remarkable capabilities practical and, accessible for real-world scenarios.
So, okay, let's unpack this just to quickly give you the gist of what we're diving into today. This paper directly confronts the major bottlenecks in VGGT, which is a leading model for 3D vision. It's incredibly good, right? But for anything beyond a short video clip, it runs into serious trouble. It's agonizingly slow and often crashes due to memory limits. The authors made a brilliant discovery, a surprising amount of hidden redundancy within the model's attention maps, a phenomenon they've aptly named token collapse. Their ingenious solution, Fast-VGGT, introduces a novel, training-free token merging strategy uniquely designed for 3D architecture. And the results? Well, this model can now process long videos up to 4 times faster, it avoids those frustrating crashes, and it even maintains, or in some cases improves, accuracy. This isn't just an incremental tweak, it's about taking cutting-edge 3D vision from like a laboratory marvel to a practical, scalable tool for the real world.
And that's exactly what we're here to explore. We'll delve into the specific architectural challenges of VGGT, how the authors meticulously identified the core problem. They were essentially picking inside the model's brain to visualize attention patterns, which is pretty cool, and then the clever, tailored solutions they developed to achieve these really impressive gains. By the end of our discussion, you'll have a thorough understanding of this crucial advancement in 3D AI.
Okay, so let's start with VGGT itself. For those who might not be intimately familiar, what exactly is VGGT and why has it become such an important player in the 3D vision landscape?
Right, so VGGT, or Visual Geometry Transformer, is a transformer-based feed-forward architecture. What that basically means is it directly infers key 3D attributes from images in a single pass. Think of it like this. You show it a couple of images, and it immediately starts to understand the camera's precise position, the depth of objects in the scene, and it can even track specific points in 3D space across those images. This direct inference capability makes it state-of-the-art for stable and highly accurate 3D scene reconstruction. It effectively handles those complex geometric relationships across multiple image pairs with impressive precision.
It sounds incredibly powerful, almost like a superpower for machines to understand geometry.
Mm-hmm.
But you mentioned a but earlier when it comes to scalability. What exactly is the problem, especially with long video inputs?
It is powerful, but that's where the scalability bottleneck emerges, particularly for long sequence image inputs. Like continuous video footage from a drone or maybe a prolonged AR session. The paper pinpoints 2 critical bottlenecks. First, the prohibitive computational costs. VGGT's reliance on what's called dense global token interactions, that's how it establishes relationships across many views or frames, leads to a massive computational overhead.
And when you say dense global token interactions, what does that actually mean for the computation? Is it linear or something worse?
Oh, it's definitely worse. The core issue is that the computational cost for its global attention mechanism isn't linear. It grows quadratically. Think of it this way. If you double the number of pieces of information it has to process, the computation doesn't just double, it quadruples. We describe this as ON squared, where N is the number of tokens, the pieces of information. This makes it an immense bottleneck, especially as the inputs get longer. And even advanced techniques like flash attention, which are great at reducing memory use, don't fundamentally change this quadratic time complexity.
Wow, okay, ON squared is... Yeah, that's rough for long sequences.
Exactly. And what's fascinating here, and truly striking if you look at Figure 2 in the paper, is how the global attention module's computational cost absolutely explodes as you feed it more input frames. For instance, processing just 20 frames, it's, a minor contributor taking about 20 milliseconds, which is nothing. But jump to 200 frames, and that same global attention skyrockets to nearly 7 seconds, that's 6,921 milliseconds. It just completely dominates the entire process.
This is an astonishing jump in computational cost. It really underscores the problem. Given that, does this paper suggest we've been fundamentally misapproaching global attention in 3D models, or is this more of a unique challenge to VGGT's specific architecture?
Well, it definitely highlights a universal challenge for transformer-based architectures with global attention when you apply them to long sequences. I mean, global attention is excellent for capturing those long-range dependencies, that's why we use it, but its quadratic scaling makes it inherently problematic for large N, for lots of tokens. This paper explores how to make that global attention smarter by identifying and eliminating redundancy, rather than just, abandoning the concept entirely.
Got it, so that makes sense. That's the first bottleneck, the computation time. What's the second major limitation identified by the paper?
The second one is susceptibility to error accumulation. As the token space expands with more frames, those minor inaccuracies that inevitably creep into the global attention mechanism, which is so crucial for interframe relations, they get amplified over time. The authors describe this as prediction drift.
So it's like a tiny mistake early on that just compounds and derails the whole system further down the line.
Exactly. It's like a small error in the initial calibration of a long-distance navigation system. The longer you travel, the further off course you get. It leads to a distorted final result in the 3D reconstruction.
And here's where it gets really interesting on a practical level, right? The original VGGT actually suffered from outright out-of-memory, or OUO, errors when trying to process sequences beyond approximately 300 images. If you look at Figure 1 in the paper, you'd see a clear demarcation line right around that 300 frame mark. It just stops.
Yeah.
This severely limited its real-world applicability for large-scale scenes, like, say, mapping an entire building or processing a truly long video segment.
Right. And this raises an important question. Can this computational inefficiency and this memory wall be mitigated without compromising VGGT's powerful capabilities? The paper's authors didn't just guess. They embarked on some clever detective work. They started visualizing the attention maps within the global attention module itself.
Ah, the visualization part. And this is where that detective work truly paid off. By looking at the global attention maps, almost like peeking into the model's thought process, they made a crucial discovery. The patterns of attention across many tokens exhibited a remarkably high degree of similarity.
It was as if multiple parts of the model were all pointing at or focusing on essentially the same pieces of information over and over again.
Okay, so lots of redundancy. They brilliantly dubbed this token collapse. It's like having several redundant signals conveying the same message.
Exactly. And this observation of feature degradation or attention similarity has actually been reported in other models, like the Dino series. However, it's crucial to understand why its interpretation and utility are actually quite different, and in fact, beneficial for VGGT. See, in a model like Dino, this kind of loss of local consistency can actually hurt dense prediction tasks, where every fine-grained detail is paramount. But in VGGT, the model has a clever two-stage design. Global attention first, then frame attention. The authors argue that this toper collapse in global attention isn't a flaw, rather it can be interpreted as a deliberate distillation of global semantics. The redundancy, instead of being a problem, actually exposes a significant opportunity to reduce computation without losing crucial high-level information.
So, if there's all this redundancy, what does that all mean for a potential solution? It sounds like the redundancy they observed opened the door to adapting token merging, a training-free technique that essentially consolidates redundant representations. It's a smart idea, but what made directly applying existing 2D emerging techniques so difficult for a 3D model like VGGT? What were the unique pitfalls they encountered?
That's an excellent question. The challenge is that unlike 2D tasks that usually process single images in isolation, VGGT fundamentally relies on robust cross-image correspondences and multi-view sequences to build its sophisticated 3D understanding. If you just naively merge tokens, you risk destroying those critical spatial and temporal relationships that knit the 3D scene together.
Ah, okay, so you might merge away something important that links two frames.
Precisely. The paper demonstrated this clearly in Table 1. Simple, random, or fixed-stride sampling methods for token merging did reduce inference time, sure, but they significantly degraded reconstruction accuracy. We can see this in their experiments where the chamfer distance, which, for our listeners, is a standard metric. It measures how accurately two 3D shapes match up. Lower is better. Well, that distance increased dramatically. Those simple methods just failed to preserve VGGT's powerful performance.
So a brute force approach wasn't going to cut it. That's where Fast-VGGT comes in as the novel solution. It's specifically tailored for 3D architecture, designed to overcome these very challenges.
Exactly. Its innovation lies in a carefully designed token partitioning and merging strategy. If you could visualize it, like in Figure 4, you'd see this strategy is guided by 3 core principles. First, rigorously preserving cross-frame correspondence to maintain structural consistency throughout the video. Second, ensuring uniform merging within each frame to avoid overcompressing and losing important areas. And third, intelligently merging the most redundant tokens into the most representative ones to maximize acceleration without sacrificing data integrity. To do this, they categorize tokens into 3 types: salient, destination, or DSD, and source, SRC.
Okay, let's break down those strategies one by one. How do they handle the reference tokens? That sounds important.
Yes. Strategy 1 is reference token selection. Tokens from the very first frame are designated as high-priority destination tokens. This is absolutely crucial because the first frame acts as the global reference for the entire scene, and their attention map visualizations showed much stronger activations towards it, ensuring reconstruction stability. So these foundational tokens are deliberately kept safe, exempt from merging.
Makes sense. Protect the anchor point. And then even within each frame, you need to make sure you're not merging away crucial details, right? That sounds like salient token selection.
Precisely. Strategy 2. To maintain global consistency and preserve fine-grained details, they identify and retain salient tokens. You can think of these as the important key points or distinctive features in each frame. These are also excluded from merging and participate directly in attention. Initially, they explored a top-CAC strategy based on token norms, selecting the most active tokens. But for better efficiency and practicality, they adopted a fixed stride sampling. This scheme retains about 10% of tokens per frame as salient, and it achieves comparable accuracy at a much lower computational cost. So, smart trade-off.
Okay, reference token safe, salient token safe. And finally, for the rest of the tokens, there's a uniform token sampling approach. How does that work?
Yes, strategy 3. Within each subsequent frame, after handling the reference and salient tokens, the remaining destination and source tokens are assigned using a region-based random sampling strategy. What they do is partition the tokens within a frame into a 2D grid, almost like image patches. Then they sample destination tokens with a predefined merging ratio and stride K within each cell of the grid. This ensures a spatially balanced merging, preventing critical information loss or visual artifacts, like parts of the scene suddenly disappear or becoming distorted. It keeps things even.
Okay, so once those tokens are partitioned, and we know which ones are being targeted for merging, the source tokens, and which are staying, destination and salient, how does the actual merging and then unmerging work? It sounds like a sophisticated compression and decompression almost.
The merging procedure is actually quite elegant conceptually. Imagine you have a lot of similar messages coming in. These are your source tokens, X. Instead of keeping every single one, you find the most representative existing message that's your destination token, 8D, that's most similar. They use K-sign similarity to check how alike their meaning or features are. Then you simply update that representative message by basically averaging it with the new similar message, XD equals XD plus X is 2. The original redundant source token is then temporarily set aside, effectively shortening the sequence length the model needs to process for global attention. It's smart dynamic data compression.
Right, makes the attention calculation much faster, and then it needs to be unmerged for the final output, right? Because for a 3D reconstruction, you need dense predictions for every part of the original scene. You can't have gaps.
Exactly. You need predictions for every original token position. So they use an unmerging procedure. It essentially replicates the merged representation back to restore the original sequence length. For example, if 2 tokens by 1 and by 2 were similar enough to be merged into a single representative token, let's call it a 1, 2, then during unmerging, both the output token corresponding to of a 1, let's call it a 1, and the one from or by 2 are set equal to that merged representation, like 1 and 2. So I 1, 1, and 1, 2, and my 1 is 2 by 1, you're 2. This preserves the token count for the decoder to produce those dense outputs across the entire scene without losing spatial resolution.
Clutter. The critical point before we get to the dazzling results is something you alluded to earlier, the VRAM-efficient implementation. We call VGGT. You mentioned the original VGGT would crash around 300 frames. How did they solve that fundamental memory limitation to even allow for these larger scale experiments with Fast-VGGT?
Yeah, that was a huge practical limitation. The authors made a clever observation. VGGT has 24 encoder blocks, right? But during inference, only the outputs from a few specific layers, specifically layers 4, 11, 17, and 23, are actually required by the rest of the model for the final output. The original implementation, however, stored intermediate results from all 24 blocks in VRAM, which is incredibly inefficient, just wasteful. So they introduced a simple but highly effective optimization in VGGT. It discards those unused intermediate outputs during inference, doesn't keep them around. This simple trick dramatically reduces memory consumption and, crucially, allows VGGT to process over 1,000 frames without hitting those O errors. This wasn't the core token merging contribution of Fast-VGGT, but it was a foundational step. It made it possible to even conduct the large-scale experiments and truly test Fast-VGGT scalability.
That's a great example of an engineering insight enabling scientific discovery. Yeah. Okay, fantastic. Now let's delve into these results because they are genuinely impressive. Fast-VGGT was rigorously evaluated across ScanNet 50, 7 scenes, and NRGBD datasets, tackling tasks like 3D reconstruction and camera pose estimation, all using their VRAM-optimized VGGT as the baseline. What did the numbers tell them?
Quantitatively, the results are striking. Let's start with the speed up. If you were to look at Figure 1, the comparison graph of inference times, Fast-VGGT's performance curve is dramatically lower. It's just significantly faster. Specifically for sequences with 1,000 input images, Fast-VGT achieves a remarkable 4x speed up over VGGT. To put numbers to it, Fast-VGT took about 180.7 seconds compared to VGGT's 724.6 seconds for the same task. Huge difference.
A 4x speed up is a huge lead, yeah. But speed isn't everything. Accuracy is paramount in 3D reconstruction. Did they manage this without sacrificing quality?
Absolutely, and this is maybe the most impressive part. On reconstruction quality, measured by chamfer distance again, lower is better. Fast-VGGT actually maintains or even improves accuracy compared to VGGT. For those same 1,000 images, Fast-VGT yields a chamfer distance of 0.425, which is better than VGGT's 0.471. This is a critical finding, demonstrating that it's not just faster, but also highly accurate. And crucially, it effectively mitigates that prediction drift we talked about earlier, limiting error accumulation in long sequence reconstructions, improving its robustness and scalability.
So faster and potentially more accurate, especially on long sequences. What about camera pose estimation?
Similar story there. For camera pose estimation, which involves determining the camera's exact position and orientation, Fast-VGGT also shows improved performance for long sequences. You can see this in Figure 5 and Table 5. For 1,000 frames, the absolute trajectory error, or AE, which basically measures how accurately the camera's path is reconstructed, is a much lower 0.164 for Fast-VGT versus more 0.196 for the baseline VGGT. And similarly, the absolute rotation error, or RE, which gauges the accuracy of the camera's orientation, improved from 4.636 degrees for the baseline down to 3.862 degrees for Fast-VGGT.
But it's faster, more accurate for reconstruction, better pose estimation, and more stable across multiple key metrics, especially on long sequences. How does Fast-VGT stack up against other leading methods in the field?
Well, this is where Fast-VGGT truly distinguishes itself. Existing state-of-the-art methods like P3 and Stream VGGT often fail entirely with O narrows on long sequences, just like the original VGGT did. They just can't handle it. Other efficient methods, things like Fast3R and CUT3R, they can handle longer sequences, but they often suffer from significant quality degradation. You lose a lot of accuracy. Fast-VGGT uniquely differentiates itself by being both efficient and accurate on large-scale, long-sequence inputs. It really offers a superior balance that many previous approaches couldn't achieve.
That's a powerful validation of their design. But were there any surprises in the Ablation studies? Those often give us the aha moments, right? Showing which components are most impactful.
Indeed. The Ablation Studies, shown in Table 6 and 7, were critical for validating their choices and understanding why it works so well. For instance, in analyzing their token partitioning strategy, each step referenced token selection, salient token selection, and uniform token sampling incrementally improved performance. Just using random sampling alone, like we discussed earlier, yielded very poor results. The chamfer distance was bad, 0.947, and the ATE was high, 0.842. Just didn't work well. In contrast, their full multi-pronged strategy achieved the best performance with a CD of 0.411 and AE of 0.141. This meticulous breakdown clearly validates that their tailored approach was not just arbitrary, but essential for maintaining accuracy.
It shows they really thought through the 3D specific aspects and the merging ratio and where they applied the merging within the network. That also seems to be a key optimization.
Absolutely. They experimented with varying the starting block for merging and the merging ratio itself. What they found was that an aggressive strategy, applying a 90% merging ratio, meaning they merge 90% of the eligible tokens, right from block 0, the earliest stage in the encoder, that consistently reduced inference time the most with only a minimal impact on accuracy. This aggressive early merging is what gave them the most favorable balance of speed and fidelity. It suggests that a lot of that critical redundancy is present right from the start in the processing pipeline, so you can tackle it early.
Fascinating. So they identified the redundancy and attacked it right where it started.
Exactly. So to synthesize these insights, Fast-VGGT presents a training-free method that significantly accelerates VGGT inference by cleverly applying token merging. It meticulously identified global attention as the primary bottleneck for long sequence inputs, and then brilliantly leveraged the observed similarities in attention maps, or token collapse, to inform its highly effective merging strategy.
And for you, the listener, the key benefits are clear. Fast-VGGT achieves up to a 4x speedup on 1,000 image inputs while maintaining competitive or even superior accuracy in both camera pose estimation and 3D reconstruction tasks. Crucially, it further mitigates error accumulation in those challenging long sequence settings. This truly makes high-quality 3D vision practical at scale.
These findings truly underscore the potential of token merging as a principled yet adaptable solution for scaling visual geometry models. It makes large-scale 3D vision systems significantly more practical for real-world applications, moving them beyond the lab environment.
What a deep dive. We've seen how pinpointing a key bottleneck and then creatively adapting an existing technique with tailored insights can unlock immense scalability and efficiency in a cutting-edge AI model.
Indeed. This work is a testament to the power of really understanding the underlying mechanics of these foundation modelers and not just accepting their limitations as given. It makes you wonder.
Yeah, it really does. And this raises an important question for you, the listener, to maybe mull over. How might these training-free token merging principles be applied to other dense prediction transformer tasks? Or even multimodal foundation models facing similar scalability issues? What other hidden redundancies are waiting to be uncovered in the vast landscape of AI models, just waiting for the right method to distill them? The future of efficient AI might be less about building bigger and more about building smarter by finding and removing that redundancy.
A very interesting thought to ponder.
We highly encourage you to check out the paper and the code if you want to dig even deeper. You can find links in the description. Thanks for diving deep with us on AI Paper Podcasts.